Hi everyone, thanks for watching. In this video, I'll explain how chemical reactions happen with something called the collision theory of reaction rates. Remember that we've already seen a chemical reaction is a change in matter where a series of things happen. One, we need bonds between the reactants to be broken, allowing the atoms to rearrange so we can form new bonds. Like here with Mg and HCl, the H and the Cl have to separate from each other so the two chlorine atoms can reattach, forming new bonds to the magnesium, and the two hydrogen atoms can attach to each other. This of course forms new substances as products. What we haven't said is exactly what causes these bonds to break in the first place. And that's where we need the collision theory of reaction rates to explain exactly how this happens. We're going to model the process with the reaction between NO, nitrogen monoxide, and O3, ozone, to look at some of the aspects of this theory. So the first part of the theory says that reacting particles must collide with each other in order for the reaction to happen. So my NO and my O3, which are both gases, that means they're going to be moving around a lot. If they move enough, eventually they'll collide with each other. So let's start them moving and see that process happen. Here they go, and eventually they smash into each other and we get our collision. Now, if that collision has enough force behind it, it will allow the bonds to actually break. Here, the bond between these two oxygens is going to break. That oxygen atom snaps off, reattaches to the nitrogen atom. If you do that, we've formed our products, NO2 and O2. So the reaction has taken place only because the collision happened. Now I want to rewind this reaction back to before the collision took place. So I'm going to bring my reactants back because there's some other aspects to this collision theory. For the next part of the collision theory, we have to realize that not all collisions actually result in bonds being broken and the reaction happening. Here I'm going to have my NO and my O3 move towards each other and collide again, but this time notice how slowly they're moving. If they're moving slow enough, the collision might happen, but this time they were moving so slow that there wasn't enough force behind the collision to actually break that bond. That means they'll bounce off of each other having collided, but the oxygen didn't attach to the nitrogen. We didn't get a reaction to take place at all. The second part of the collision theory factors this in and says that particles must not only collide with each other, but they must collide with enough energy to actually start the breaking of bonds and the forming of bonds. And this amount of energy that they must collide with has a name. It's called the activation energy. For the last part of collision theory, we've got to realize that not all collisions, even if they have the correct amount of activation energy, will result in bonds being broken and the reaction happening. To see how this works, I'm going to put two different versions of this collision between the reactants side by side with each other. So let's bring those molecules towards each other. Here they are moving, and here the collision happens, but notice the way that they collide. The nitrogen atom has to collide with the O3 in order for the reaction to happen. Here, the collision on the bottom, the nitrogen atom is the atom that collides with the O3 ozone. Up here, the collision happens, but not with the nitrogen. Here, the molecule has twisted around differently so that it's the oxygen colliding with the O3. Since the nitrogen is the one that has to collide with the O3 to get the reaction, this collision results in the reaction happening, but the one on top does not. As they separate from each other after the collision, the one on the bottom has produced our products, but the one on the top did not. The final component of the collision theory ties this in and says that particles must collide with the proper orientation. And orientation is just a fancy way to say that the correct atoms have to be pointed towards each other in the collision to get the reaction to happen. So let's close this video out by putting all three of these components side by side and actually saying what these collision theory elements actually have to do with a reaction rate. A rate meaning, does it go fast or slow? The rate of reaction is proportional to the number of effective collisions between the particles. Now that sounds kind of confusing. All it means is that the more effective collisions you have, that's going to result in a faster reaction. So the more collisions there are, as long as those collisions are effective with enough energy and in the proper orientation, means your reaction goes faster. If there are fewer effective collisions, either they collide less, or when they do collide, they don't have enough energy, or they're not in the proper orientation, the fewer of those collisions there are, the slower your reaction is going to go. so we can use this collision theory to explain why some reactions go more slowly and others go more quickly. That concludes this video. Here's a brief summary.